In this video, we will discuss the perturbations theory. Now we first define what is perturbations. So in a quantum mechanics, when a system is disturbed, then the wave function and energy of a system is changed. When a system is disturbed, then the system wave function and energy may change, and this change in a system is called perturbations. Okay, for example, let's suppose we can consider the infinite sphere well like this, from 0 to a. When we perturb like the system this is the perturbation. Okay, now we can consider the another way is like this, and here the perturbation is like this. So from 0 to v0 to this point, this is a perturbation. Okay, so when we perturb this system, then this system wave function and energy may change, and this change in a system is called perturbations. Okay, now the other one, now we discuss the perturbations theory. Okay, the perturbation theory is the systematic procedure to obtain the approximate solution to the perturbed system. This is a perturbed system like this is a perturbed system, this is a perturbed system. So we can apply this perturbation theory to like this system to obtain or to find the approximate solution to the perturbed system. Okay, this is a perturbed system. So we can apply this perturbations theory to find the approximate solutions of the like this system when we perturb the system. Okay, now we can divide the perturbations theory into the two types depending upon the nature of problem. We can say that like this perturbations, like this perturbation. So this is depending upon the nature of problem, this and this. So they can divide into the two types. The one is the time dependent perturbations theory, and the other one is the time independent perturbations theory. Okay, in this case the Hamiltonian depend upon time, because this is the time dependent. In this case the Hamiltonian of a system does not depend on time. Okay, so this time dependent perturbation theory discussed in the next chapter, and this topic and discussed in this chapter, the time dependent perturbations theory. So, and this time independent perturbation theory further divide into the two types. The one is the time independent perturbation theory of the degenerate state, and the other one is the time independent perturbations theory of the non-degenerate perturbation non-degenerate state. Okay, so now we can define this the degenerate states if the two or more unperturbed states. Unperturbed state, let's say psi1, psi2, this is the unperturbed state, have a same energy, let's say E1, so then they are said to be a degenerate states. And this means that the one energy value can have many wave functions. Okay, now the non-degenerate states, if the two or more unperturbed states, let's say psi1 and psi2, this is a two unperturbed states, can have a different energies though. Let's say E1 and E2. Okay, this means that for every energy value can have a corresponding energies, a corresponding wave function, sorry, a corresponding wave function. For every energy value can have a corresponding wave function. For example, the E1 can have a corresponding wave function psi1 and similar for the psi2. Okay, now we discuss the perturbations theory, the non-degenerate perturbations theory of perturbations theory. Okay, for this purpose we suppose the one-dimensional of the infinite sphere well for 1D, the infinite sphere well have a potential is H naught and psi n naught is equal to E n naught and psi n naught. Okay, this is the a potential for the infinite sphere well and the unperturbed states. Okay, when we perturb the system, then the new eigenvalue and eigenfunctions are is H and psi n and E n and psi n. This is for unperturbed. Okay, and this is for a perturbed system. So then the total Hamiltonian is H naught, this one, plus the change in the system of the Hamiltonians. Okay, now there here lambda is a small quantity. To find the approximate solution to this perturbed system, we will apply the perturbations theory to find the approximate solutions. Okay, now we can write E n and psi n has a power series in lambda. let's say now we can, this is En naught plus lambda and En1 plus the lambda square and En2 and so on. And for psi is En naught plus the En1 and here lambda plus lambda square and psi N2. Okay. Now we can put these value into these equations. Okay. To find the approximate solutions, now we can put H naught plus H dash into psi is psi N naught into lambda into psi N1 plus lambda square and psi N2 into En naught plus the lambda and En naught plus the lambda square and En naught, this is 1 and this is 2, and then the wave function is En naught plus lambda and En1 plus lambda square and psi N2. Okay. Now we can simplify these equations, and first we multiply this H naught to all these terms, then H naught and psi N naught plus the lambda and H naught and psi N1 plus the lambda square and H naught and psi N2 plus, we can multiply this term to all these terms, then lambda and H dash and psi N naught plus lambda square and H dash and psi N1. The other term is to be neglected because the lambda is a small quantity, so the higher power are to be neglected. Okay, and then is equal to, now we can multiply this term to all these terms of the wave functions, then En naught and psi N naught plus lambda and En naught and psi N now 1 plus lambda square and En naught and psi N2 plus the, now we multiply this term into only these two terms, and lambda and En naught and psi N naught plus lambda square, and this is 1, this is not 0, and En1 and psi N1 plus, well, now we can multiply this term only to this term because the higher term are to be neglected, lambda square En2 and psi N. Okay, now we can rearrange these equations. This is equal to H naught and psi N naught, and then plus lambda can take common from this term and this term, and then it's H naught psi N1 plus H dash and psi N0, and then I can change color, and we can take common lambda square from this term and this term, not this term and this term. Okay, is H naught and psi N2 plus the H dash and psi N1 is equal to En naught and psi N naught N plus and then we can take common the lambda from this term and this term, and then e in 0 and psi in 1 plus the e in 1 and psi in 0, then plus we can take lambda square from this term, this term, this term, three terms is e n naught and psi n 2 plus the e in 1 and psi n 1 plus the e n 2 and psi n 0. Okay, now we can only compare this equation both sides, then this two are equal because here the lambda are 0 and here also is 0, then h naught and psi n naught is equal to e n naught and psi n naught. Okay, and this is the exact solution for infinite sphere. This is the unperturbed state for infinite sphere. Okay, now we can compare this two, then h naught and psi n 1 plus h dash and psi n 0 is equal to e n 0